Okay. Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to all of you. So this is our first real meeting, okay, for SEE4433. Sorry for that. That one is for the old code numbers. Okay, so you are the batch, the newer batch, which is SEE4433. Okay, for those who are online, can you hear me? Sure. Okay, thank you very much. So this is the first experience where we have hybrid class. So I hope since the Wi-Fi is good, so I think it should be continue like that lah. Okay. Okay, so we are in the third chapter. Okay, so DC converters. Okay. So what is a DC converters? So this is actually the second converter that we will learn. Okay, the first converters is actually a rectifiers, right? Which is we convert from AC to DC. It can be a single phase and it can be a three phase. Okay, and then the application of the rectifiers is a very numerous applications. Okay, you can control the, for example, the light, the fan, the motor drive, and so on. Okay, so this one is the second converters, which is a DC converters. What it actually did is actually it convert a DC voltage, unregulated DC voltage, okay, into a regulated DC voltage. For example, your load requires 5 volts, but your input is 10 volts. So how can you regulate? Okay, so you step down to 5 volts or so on. So that is what we call regulation. Okay, so DC converter is actually it regulate the DC voltage that will suit the load. Okay. So the other name of the DC converters is actually what we call a voltage regulators. Okay. I think you have maybe know about this voltage regulator name during your electronic subject. Pernah dengar tak? Have you heard about voltage regulator? It's not bukan yang untuk komputer tu kan?
It's a Zener diode.
Sorry?
Zener diode.
No. It's actually a chip. Integrated chip. Yeah, I see. Voltage regulator. But that one is totally different from voltage regulator that based on power electronics. It's very different. Okay, I will tell you what is the difference after this. Okay, and typical application, I hope you can see this, which is the SMPS, which is the switch mode power supply. Okay, for example, it's actually the DC power supply that in your lab right now. Pernah masukkan lab power electronics? Pernah kan? Ataupun ada labs? Tak pernah nampak voltage regulator, DC power supply. For those who have went to power electronics lab experiment, do we have a DC power supply? Ada? Tak nampak yang ada knob tu? You boleh adjust the voltage of that one is actually a switch mode power supply. One of our application where you have a DC power supply, DC converters there. And then the second application is the motor controls, and the last one is battery chargers lah. So actually there are a lot of applications lah. So this is one of the examples. Okay. So this is the typical block diagram that shows the DC converters, where the input is actually unregulated DC input that can come from your rectifiers. Okay, because we know rectifiers convert AC to DC, right? So the input can become from the output of the rectifiers. So and then maybe you want to regulate, maybe to step down or step up the voltage to meet the DC load. Okay, and then this one you have a signal controls lah here. Okay, which is come from your feedback circuit and so on. Okay. So this is the basic linear regulator that I have what I call cakap dengan tadi tu. A simple chip, integrated chip that you have learned during your electronic subject, I think. This is actually a basic linear regulators that inside the chip. Okay, where as you can see here, for example, susah juga ni because I need to attain two type of student. The first one is the physical student, and the second one is the online student. Ini macam mana ni? Nak tulis tak nampak pula kat sini. Okay, for example, this one is your input is lain For example, this one is 100 volt. Okay, but your load requires only 5 volts. So how can you convert from 100 volt to 5 volts? Okay, so for the basic linear regulator, what it did is actually they are using transistors. But this transistor, as you maybe recall, we have two regions, right? Ada three regions. For example, transistor. You have this one apa? Collector. This one emitter. This one is your base lah. Okay, so this one is BJT lah, right? BJT. Kalau MOSFET, if MOSFET for example, drain, this one yang bottom, source ataupun sink S. This one, okay, so this one is your VGS and this one is your VDS. Okay, and the current here is your I drain. Okay, and then this is IG. So for the characteristic, the output characteristic for the MOSFET ataupun IGBT lah. So this one is a IGBT, sorry. This one is IGBT. Okay. So this one is your apa dia? I drain. This one VDS kan? And this one is your VGS. Okay, VGS1, VGS2, VGS3. So we have three region, right? We can divide into three region. This one is what I call? What region is this? For the transistors. Oh, current mengalir. You have a current flow here. This one ID, meaning that there is a current. So this one is saturation, meaning that the switch is on, right? And this one, this region, the current is almost zero. So this one is cut off region, okay? And then another region is at the center, which is, we call this one active region. Okay, so in electronics, basic electronics, your lecturers always say that don't operate your transistor under saturation or cut off, right? Because for electronic circuit, their aim is actually to use transistor as amplifiers, right? So that's why their circuits is more on how to operate your transistor inside the active region. Okay, but in powertronics different. Powertronics actually used as a switch. So either on or either off. Okay, so by using the electronic basic linear regulators, so this transistor is operated under active region. active region. Okay, so as you can see, if you operate under active region, when you change something, for example, the current, the voltage will change, right? So we always represent the transistors, if these operated under active region, it is always referring as a variable resistor. Okay, because once you change the current, you change the voltage. Okay, so what is the drawback or the limitation of using this basic linear regulator? It's very simple. The advantage is very simple, but there is one big problem with this basic linear regulator. From here, what you can see, for example, the input is 100 volt. The input that requires only 5 volts. Your load requires only 5 volts. For example, your radios, right? 5 volts. So what can you see from this circuit? What is the problem with this circuit? This one, 100 volt, but you only requires 5 volt only. What happened to other 95 volt? It's actually drop here, right? So 95 volt. Can you imagine the current that flow here? What is the current? So meaning that this one, the power losses is V multiplied with the current, right? The voltage drop here is 95 volt. Multiply with the current, so you can see how much power losses that from this circuit. For example, the current here may be 5 amperes, right? Depending on the load and so on. So 5 amperes. So you just multiply 95 volt with 5 amperes. So you will have berapa? 100 something, right? What? So that is losses. You boleh kira berapa? 95 kali 5 berapa? Huh? Okay, so power loss is 475 watt. Okay, and your P out berapa? 5 kali 5. 5 volt multiply with 5 amperes. 25 watt. So the efficiency P out over P in kan? Berapa? P out over P in. Your P out is 25 watt. Your P in is 100. 100 multiply with 5. So 500 watt. Berapa? 25 over 500. 0.05. So only 5%. Efficiency is 5%. Very low. So very low. So we don't want this because right now we know that our energy source is depleting, right? The what called the fossil fuel and so on. So depleting. And then so we are actually want to use the energy as efficient as possible. So we want to minimize all the losses. Okay? So that is where the power electronics advantage. Okay? We reduce the losses. Okay? So by using these basic linear regulators, which is a basic electronic circuit, you can see that the limitation of this is actually in terms of the efficiency. It's not very efficient. Okay? It's not very efficient. So this slide shows about the losses lah, okay, that I have already described. Okay, so right now, so you can see the what is the limitation lah because of the losses and so on. Okay, and then so that's why we are using the same circuit, but the transistors right now are operated as a switch. Same transistors, which is you can use IGBT, you can use MOSFET, or you can use BJT, but different region. We are using it as a switch, on and off. Okay. So meaning that if this switch is ideal, so we know that when the switch is off, so no current will flow. No current. So I is 0. So the power across this one will be 0. Same with when the switch is on. So we consider that there is no voltage drop, and so still during switch on and switch off, there is no losses at this switch. Okay, so power losses is 0 watt, meaning that the efficiency is 100%, meaning that your P in is equal to P out. So we want that. Okay, using the same transistors but different operating region. Okay, faham Understand? Okay, so we will introduce you the type of DC-DC converters. So this is the class of the DC-DC converters. We divided it into two classes. The first one is the non-isolated. Okay, meaning that there is no transformers between the source and also the load. Okay, so we from here, tak nampak sorry for that lah, because this one is uncontrollable. Tak boleh. Nampak tak? Sebab saya punya screen ni putih, my background is white. So this one is non-isolated, no transformers, and this one is the isolated, meaning that you have a transformer between the source and the load. Okay, so in your syllabus, we only concentrate on non-isolated only. Buck converters, which is a step-down converters, and then we have a boost converters, which is a step-up converters, and the last one is the buck boost, meaning that it can step down and it can step up. So we are only concentrate on these three non-isolated converters only. Okay. This one, isolated, we only just give you a brief introduction about this type of converters. Okay, we have the flyback converters, forward converters, full bridge, and half bridge. But this isolated, if you compare isolated and non-isolated, so the isolated converters is more appropriate to be used as a power supply because it has isolation. Okay, so in terms of security, so the isolated version is much more preferred. So that's why they are mostly used for the DC power supplies. Okay, for example, if you have, for example, your laptop chargers, okay, all inside that chargers, you have a DC-DC converters, right? You have rectifiers, AC to DC, and then you have a DC to DC. So usually for that part, DC to DC converters, usually they are using flyback converters. This one, the first one. Okay, flybacks. For the Apple products, for example, MacBook and so on, the chargers, they are mostly flyback converters. Okay, but it's a very complicated circuit, so that's why we only just, actually for our previous batch students, we do some calculation here. Okay, very deep, but because right now we want to differentiate the master level and undergraduate level, because for master levels, master student by taught course, we are also offering the same subject, the same course, power electronic system. So the content is same. So to differentiate between the master level and undergraduate level, so we take out this content from the undergraduates. So we only concentrate on buck converters, boost, and also buck boost. Okay. Okay, boleh So we go for the first converters, which is the buck converters. So buck converters is a step-down converters. So it consisted of 3 elements: the diode, inductors, and also the capacitors. And since this is a step-down converters, so your V out is always lower than V input. Should be like this. So this is wrong. So should be V out is always smaller, or you can also equals to your V input. Okay, it can equals to V input. So this is a switch. Should be transistors, okay? It should be transistor. You cannot use SCR. Because this one is a fully controlled. The switch must be fully controlled, meaning that you can control the timing on or off. SER, you can only control on, right? Only. So, but for this circuit, you need to use a power switch that can be fully controllable, on and off. So the only device that suitable for this is transistors. You can either use IGBT, MOSFET, or BJT and so on. All type of transistors. So the circuit can be, this switch can be on and off. Okay. So meaning that you need to analyze the circuit in two states. The first state is when the switch is on. What happened to the circuit when the switch is on? And what happened to the circuit when the switch is off? Okay. Because the behavior of the circuit during these two stages are totally different. Okay, so let's see or analyze what happened when the switch is on or the switch is closed. So when the switch is closed, you can see that the diode is in reverse bias. Okay, oh ya, ada local student yang tak datang ke? Kenapa dia? For local student, we are forcing them to come into UTM lah. So the online platform is only for the student who are not able to come. Usually for the foreigners lah, kan? Tapi tu ada local student yang masuk sini. Ada yang tak datang lagi? Your friends, local, tak kenal? Tak kenal? Ada kan? Sebab ada yang masuk ni. Ni Nur Hazika. Ada? Kenal? Tak kenal? Yes, recorded. Susah sebenarnya nak, it's very quite difficult lah to maintain focus for the class and then focus. Sorry for the online students. Okay. So when the switch is closed, so what happened when the switch is closed? So the diode is reverse bias. Reverse bias meaning that the diode is off. Why the diode is off? Why the diode is reverse bias? Why the diode is in reverse bias? What is the condition when diode is reverse bias? The anode and cathode, you see the polarity of the anode and cathode. When forward bias, the anode must be more positive compared to cathode. So right now in the circuit, right, the diode is actually like this. What can you see in terms of the polarity of the anode and cathode? Which one is much more positive, anode or cathode? So this one is your cathode, this one is your anode. Yeah, cathode is positive, right? Because it directly connected to your voltage source, right? So this one is positive, this one is negative. So cathode is positive compared to anode. So that's why the diode is reverse bias. So reverse bias, so and then we represent as a open circuit. And the rating of the voltage, the rating of the diode, when you want to select or you want to buy what rating of the diode, the rating of the diode should be equals to your voltage supply. Okay, this one. Okay, V rating of the diode is equals to V supply. Because diode, you have a lot of ratings, right? So to select the diode rating, for example, for the voltage rating, so you need, for this one, you need to look at what is the voltage across the diode when this diode is off. So which is, in this case, is equals to voltage supply. Okay, when the voltage supply is 100, but you use diode rating 10 volt, low lah. For the hardware, memang terbakar, broken. But in simulation, you cannot see that. Kan? Okay. So the diode is in reverse bias. And the current will actually flow through the inductors. Okay. And then you have this one is your I out. You have this one is your I capacitors. This one is your IL. Sorry, this one should be still in time domain. Okay, time domain. So ILT. So all must be have a time domain there. ILT, I out T, and ICT. Okay. And the voltage across the inductor right now, what should be the voltage? So this one is not Vs, and this one not is a V out. So your voltage inductor is Vs minus V out, right? Vs minus V out. Okay. And as you can see, so this one, okay, this is the time. This one when the switch is on. So you can see the waveform. This one is your VL. So we assume that this one is the buck converter. So we assume that Vs is always larger than V out. So that's why we have a positive. Okay. Mana ni? Mana saya punya mouse tak keluar? Okay, positive Vs minus V out is positive because this is buck converters. Input is larger than V out. So that's why we have positive. Okay. And what about the waveform of the current, inductor current here? So the inductor current, so actually it is actually a linear increment. Oh, saya kalau tunjuk kat sini, dia tak keluar kat sini. Tak nampak Okay, linear increment in the IL, which is positive ramp. Positive. Okay, so it increased from I min into a maximum values. So why it is a linear increment? Because you can see this from this equation. VL, which is the voltage across the inductor, is L di over dt. Okay, and then you manipulate this one, so you get the IL. So your IL is actually equals to 1 over L integration of VL. So right now your VL is a constant, right? Positive. So you integrate a constant, you will have actually a linear increment, positive. Okay, so that is actually when the switch is on. So you need to know the VL values and then the current values. Okay, so this one is very important. You need to know this. Faham? Understand Kalau tak clear, you can raise your hand. Before we move to the when the switch is off, what happened? Berapa orang online ni? 3 orang. Tadi itu dah hilang dah local. Okay. So this is actually when the analysis when the switch is on or the switch is closed. So your VL is a positive, Vs minus VO, and your current is actually a positive linear increment from I min to I max. Okay. Yang DT ni time, the time ni, time scale ni, I will explain later. So we are only concentrate on VL and IL only. Okay. So I will explain what is DT, what is T, what is 1 minus DT, and so on. So that is when the switch is on. So next is the the analysis when the switch is open. So what happened to the circuit? So right now the switch is open. So meaning that your voltage supply is right now disconnected from the circuit. Okay. So the node here is 0 volt. Okay. So right now, as you can see, the diode is in forward bias because the cathode is right now is more negative or lower polarity compared to the anode. Okay, so the diode is actually in a forward bias. And the voltage across the inductor right now, so this one is still VO. So your VL is actually 0 minus VO. Should be negative here. Okay, negative VO. Okay, VL is negative VO because this one 0 minus VO. Okay, VL is negative VO. Okay, so we are only concentrate on this, okay, this part, okay, when the switch is open. Okay, negative VO. Okay, so as you can see in your waveform here, VL, you will see that during the switch open, your VL is negative VO. Okay, negative VO. Okay, and then the current, we know that VL is L didt. So L didt is actually negative VO. So you can see that the current will be integration of negative, right? So that's why you will have, since your VO is actually a constant negative, constant value here. So integration of any constant value will get you a negative, will get you a RAM. But right, since this is a negative value, so meaning that it is going down, negative. The slope is negative. So meaning that it going down from maximum to minimum values. Okay, so we have complete the analysis. So we complete the analysis, switch on, and the analysis when the switch is off. Okay. Understand? Aku tak boleh ni. Okay. Kat sini. Apa sini? Okay. So we go back to the when the switch is closed. So what is the relationship when the switch is closed? The VL. VL is VS minus Vout. Positive, okay? Positive. Since we know that VL is L di over dt, so this one is a VS minus Vout. Okay? So, gonna erase this one. So, tadi dapat L di dt is equal to VS minus Vout. So, then di over dt is equal to VS minus Vout over the inductor, right? Okay? We just replace L here. So di over dt is actually, you know that di over dt is actually the change of current referring to the time, right? So any change, so meaning that we can just use I, L over the change of time, right? The change of current over the change of time, right? Differential. Okay. Okay. So that's why saya buat ini. The change of current versus the change of time. Okay. Boleh? So right now, for the switch on, we see that, so meaning that kalau saya lukis kat sini, so this is actually your change of IL. Bawah sangat ni. Nampak? Tak nampak eh? Kalau saya rujuk kat sini. So this is your current IL. So this one is your delta IL. The change of current from minimum to maximum. So that is your change. And this one is your DT ataupun delta T. Okay. So change of IL over change of time. Nampak eh? Saya fikir balik lah. Tahu juga. Change of IL over change of time. Okay, this one. So actually your IL is I max minus I min. Okay. So right now you can see that your delta T is actually dt. So what is actually dt here? What is dt? D multiplied with T. So we actually define something here. So your actually, this one, from 0 to dt, okay, we call this one as a T on, okay? T on. So your T on is equals to dt minus 0. So meaning that your T on is dt. Bawah sangat eh. Bila saya nampak sini nampak still saya masih lagi tinggi kat screen. Okay. So your T on is dt. So meaning that your T, D is actually T on over. So what is D? So this is a new, orang kata apa new parameters, which is D is actually what I call duty cycle. Okay, susah betul. Duty cycle, which is D. So what is duty cycle? Is the ratio of T on over T. Okay. If you confuse, so actually this one is actually, we call this one is a delta T, right? Delta T. And this delta T is equals to your, is actually equals to T on. Okay? Is equal to T on. And this T on is equals to dt. Boleh? Kan? Ataupun itu rujuk sini lah, this one. D is equal to T on over T, right? So, yalah, T on is dt lah. Okay, so during switch on, your delta T is T on. The change of time is T on. And what is your T on? T on is dt. Duty cycle multiply with period. The time period, the time full cycle. Okay. Okay, so from that, can you define this one? So right now we know that this one is T on. Can you define T off in dt? Boleh tak? You orang kata apa? Derive what is T off. Right now we know that T on is dt, right? So can you derive what is T off? What is T off? From here you can please derive. Sini. Berapa? T off. Dapat dah? Boleh angkat tangan, raise your hand. Ataupun kalau malu, you can just WhatsApp. What is T off? T on is dt, okay? What is T off? Huh? Alamak. Boleh tulis? Berapa tadi? Sebut cakap apa? Tak dengar? T minus dt. Okay, your friend said T minus dt. Is it correct? Yalah, senang lah. T minus dt kan? Memang from the waveform, you can get T minus dt. So actually, yes, your this one is correct, but you can simplify it further. Okay? So your T off is yes. Saya dengar. So your T off is 1 minus D. Kan? Okay? So alhamdulillah, so T on is dt and T off is your 1 minus D. Okay, boleh. Nak salin? If you want to copy it. Okay. Okay, so we go back to our analysis. So right now we have already know that you can di over dt, you can actually change into a delta IL over delta T, right? And we know that your delta T is your T on, which is dt. Okay? So from here, you can derive an equation that relate the change of IL. So your change of IL during switch on is Vs minus V out over L multiply with dt. Daripada sini, this one, dt you masukkan ke sini. Pindahkan. You transfer. So that's why this is a very important equation. We want to derive this equation. So the relationship between delta IL during switch on is Vs minus V out over L multiply with T on or dt. Nampak tu susah. Kalau boleh naikkan sikit. Okay, clear? Okay, this is when the switch is on. You need to know how to obtain this equation. Delta IL on. Okay. So let's look at the analysis when the switch is open. So we already know that when the switch is open, the relationship between VL and V out is this one. Okay. And then we know that VL is DIL over dt, so we can rearrange that equation into this form, which is delta IL over dt is equal to negative V out over L. And this one we can rewrite as a delta IL over delta T is equal to negative V out over L. Okay. So right now, your delta IL is actually delta IL during off, right? Over your delta T. Your delta T is T off. This one is T off. So what is T off? T off is 1 minus D T. So this one is equal to negative V out over L. So that's why you have this one. Okay, and then I rearrange this equation. So I will obtain my delta IL during off state or open is equal to negative V out over L multiplied with the T off. Your T off is here. Tengah hari ni memang mengantuk eh. Kalau nak minum boleh minum. Smoking tak boleh lah. Okay. Faham eh? Understand this one? Okay. So this is analysis when the switch is open or the switch is off. And then from that, we want to actually make some what we call conclusion. Okay. At steady state operation, the change of current inside of the inductor during on plus the change of current when the switch is open must equal to 0. This one is very important. Okay. Current start at the period must equals to the current at the end of the period. That is the condition. Okay. So from here, so we derive this one, which is all the change of the current must equals 0. Okay. And we have already know that the change of current IL during off state is this equation, while the current during on state is this equation. Negative V out over L, okay? Negative V out over L, 1 minus dt. So, if you compute this equation, you will finally obtain the relationship between V out and V in, which is V out is equals to D duty cycle multiplied with V input. Okay, this is the conclusion. From the analysis of switch on and switch off, we obtain the relationship between V out and V input. And what is D? So D is your duty cycle, which is T on over T. So your duty cycle is just a ratio, okay? So T on over T, just a ratio. Meaning that your D maximum is 1, minimum is 0. Right? When D is 1, meaning that it is fully turned on for the whole period. Okay? So from here, you can see that V out, the maximum V out is equals to V input. It cannot higher than V input. So that's why this converter we call step down converters. Okay? So yang bawah ni, the lower part here is the assumption lah. So we assume that the switch is an ideal switch. There is no voltage drop. There is no what called internal resistance. So the losses is 0. So meaning that P in is equals to P out. 100% efficiency. Okay, so we take a break 10 minutes. So before we proceed with the analysis of the IL. Okay. So 10 minutes, so 11:51. So we meet again around 12:01. Okay, can we continue? Allahu Akbar. Proportion. Okay.